Hello student, welcome to our channel Simplified Chemistry. Our today's topic is chemical kinetics. Let's start the topic. Today we will discuss about law of mass action and rate law. We already know that rate of any chemical change is equal to change in concentration of reactants or product with time. Therefore, rate is directly proportional to concentration of reactants. On increasing the concentration of reactants, rate also increases. This quantitative dependency of rate on concentration of reactant is known as law of mass action. According to this, rate of any chemical change is directly proportional to the product of active mass of the reactants with power is equal to their respective stoichiometry used in the balanced chemical equation. Therefore, for any general chemical change AA plus BB into product, rate will be rate directly proportional to A to the power small a into B to the power small b. Now, in this connection, we used a new term, that is active mass. Generally, for a real system, not all the reactant turns into product. Therefore, the concentration of the reactant actively participate in the product formation is somewhat less than the given molar concentration. Therefore, in the statement of law of mass action, we used the active mass of reactant, not the mass of the reactant. But it is very difficult to calculate the mass of the reactant which actually turns into product, that is active mass. Therefore, we assume that active mass is equal to given molar concentration of reactants. Now, there is a twist. According to law of mass action, rate of chemical change is directly proportional to product of the concentration of the reactants with power is equal to stoichiometry used in the balanced chemical equation. But the experimental rate equation does not match with this statement. Law of mass action derived from balanced chemical equation. It is purely theoretical concept, but from experimental data we have rate expression which is completely different from the law of mass action. For the same general equation AA plus BB equal to product, the rate from law of mass action is directly proportional to A to the power A into B to the power P. But from experimental data, the rate directly proportional to A to the power P into B to the power Q, where P and Q may or may not be equal to the stoichiometry used in the balanced chemical equation. Now, take some real example of chemical reaction when nitric oxide and hydrogen reacts to produce nitrogen and water. According to law of mass action, rate should be NO2 to the power 2 and H2 to the power 2. But from experimental data, we have rate directly proportional to NO to the power 2 into only H2, not H2 to the power 2. To understand this mismatch between experimental data and theoretical data, we have to understand another important term, that is rate determining step, or simply RD step. We already discussed that even a simple looking chemical reaction involved multiple steps, but theoretically we expressed all the chemical reaction by a simple balanced chemical equation. Each steps involved in a reaction is considered to be an elementary reaction having its own rate. So, for every chemical reaction we have more than one rate expression. Therefore, kinetic study becomes so complex. To solve out we find a shortcut. Among all the steps, we focus on the slowest step, which is known to us as rate determining step or RD step. And the total kinetic study of the chemical change is moved according to this step. Therefore, this step decides the overall rate of the reaction. As for example, when N2O5 decompose to form NO2 and O2, the decomposition takes place in two steps. In first step, N2O5, one molecule of N2O5 produce NO2 plus NO3, which is slowest step, and in the next step, N2O5 combine with NO3 to form NO2 plus O2, which is fast step. As the first step is the rate determining step and only one molecule of N2O5 participate in this step, the rate becomes directly proportional to concentration of N2O5, not N2O5 to the power 2. So, we may conclude that law of mass action is based on balanced chemical equation or theoretical concept, whereas rate law is based on rate determining step, that is experimental data. Therefore, they are differ from each other. Now, for a general reaction, AA plus BB turns into product rate according to rate equation directly proportional to A to the power P into B to the power Q, and rate is equal to some constant, that is K into A to the power P into B to the power Q, where K is known to us as rate constant and Pu and Q, the power of concentration term A and B, represent the true dependency of rate on the concentration of reactant. And this expression is known as rate law, that is the actual dependency of reactant concentration, the actual dependency of rate on the reactant concentration, which may or may not same with the balanced chemical equation. Now, let us focus on the rate constant. If the concentration of each of the reactant is unity, that is A is equal to 1 mole per liter and B is equal to 1 mole per liter, then rate is equal to K. Therefore, we can define rate constant as rate constant of any reaction is equal to rate of the reaction when all the reactants having concentration unity. Now, rate constant is a very important term in study of chemical kinetics. From the value of rate constant and unit of rate constant, we can understand the nature and the speed of the chemical reaction. The unit of rate constant is depend upon the concentration of the reactant participate in the rate equation. As for general reaction, rate is equal to K into A to the power P into B to the power Q, where A and B represent the concentration. If we assume that P plus Q is equal to N, therefore rate is equal to K into concentration to the power N, or K is equal to rate by concentration to the power N. We know the rate is expressed in mole per liter per second and concentration is expressed in mole per liter. Therefore, the unit of K becomes mole to the power 1 minus N, liter to the power N minus 1 into second inverse, where N is the sum of the power of the reactant concentration used in the rate law. For gaseous reaction, the unit of rate constant become atm to the power 1 minus N into second inverse. This rate constant bear some important information about the chemical reaction, as higher the value of the rate constant, greater is the value of rate of the reaction, and its value is highly dependent on the temperature. A particular reaction has a definite value of rate constant at a particular temperature, and the value of rate constant increases with an increase in temperature. but the rate constant does not depend on the initial concentration of the reactant, and its unit is depend on the overall power of the reactants used in the rate law. So, this is the end of our today's discussion. In the next session, we will discuss about order and molecularity of any chemical reaction. Thank you for watching. Please subscribe, share and give your valuable comment in the comment section.